Welcome back. This is Tutor Wizard. I'm Adrian. This is Alice. This is Ringo. Please subscribe right here. Hit the notification bell down there. We're going to do some more cat path feeder if I can wrangle them in. All right, let's get to it. What we're going to do today is this lecture. They're attacking me. Okay. This lecture, what we're going to do is solve second order linear constant coefficient non-homogeneous ordinary differential equations 3 ways. What? Let's get to it. All right. This is the big boy noodles. We're going to do the big boy and big girl theorem. What this says is it gives us, okay, you ready? There they go. You want outside? Just a second, we got to let noodles outside. All right, theorem. Consider the real numbers a, b, c, x naught, y naught, y1. What are these? These are arbitrary 6 numbers. A, b, c come from the coefficients in front of our ordinary differential equation. And then these 3 numbers are going to be used in our initial value problem. Y of x naught is y0, and y prime of x naught is y1. Once we have that, what we're saying is consider a particular solution to our second order constant coefficient linear non-homogeneous ordinary differential equation, this guy. And if we have a particular solution to this, which we have 2 methods of doing this, in our previous videos, go check them out. We have undetermined coefficients and variation of parameters is how you find a particular solution. But if I do have one of those, and if I have y1 and y2 are the linearly independent solutions to the associated homogeneous equation, this guy I let f be 0. And then again, we have another video on the systematic theorem, which gives you the 2 linearly independent solutions based on the roots of the auxiliary equation. Once I have those guys, and I have this guy, again, in this theorem, we're already assuming that you cooked these up and you found this. Once I've done that, using all of those other techniques in the other videos, what they're saying is there exists its existence and uniqueness. So first of all, we're saying there is a solution to the ODE, and there's only one of them. And so then students always come at me hot and be like, I switched these slightly and then I got a totally different answer. This can't be true. The theorem's saying it's unique. There's only one, like the Highlander. It might look drastically different. He's in a kilt this century and then he's in a modern clothes in another century, but it's the same dude. There can be only one. What are we saying? There exists a unique solution in this interval I to the initial value problem ay prime prime plus by prime plus cy prime or plus cy equals f. There exists a unique solution to this initial value problem, and it's given by, in particular, this. This is the unique solution, and notice I've changed the, where did they go? Oh, I didn't even write them down. But in the general solution to y homogeneous, we get c1 y1 plus c2 y2. And in variation of parameters, we actually make those functions, and this is the clever trick. But those guys, c1 and c2, are going to turn into the unique numbers alpha and beta by using the initial conditions to find them. Therefore, what I'm going to do is I'm going to use variation of parameters where I pick root 1 to be this guy and root 2 to be this guy, and then I'll solve it, the unique solution. And then I'm going to switch the roots, just in case you're like, what if I switch them? It doesn't matter. It'll fix everything. You'll get the same unique solution. And then I'll use undetermined coefficients, and guess what? You're going to get the same solution every time. It's unique. Let's do that. All right, we're back. What we're going to do is juggle some cats. Whoa, where are you going? There they are. Oh, jump. All right, what are we doing? We are solving, neither of them wants to look, and it sounds like both of them. Oh, get down there. All right, let's just try to use this one. What we're going to do is we're going to solve the initial value problem, y prime prime minus 3y prime plus 2y equals 1. If it's homogeneous, it's not so bad. You just use the auxiliary equation, you use the basic, the roots of the auxiliary equation, and then you get 2 linearly independent solutions. So I decided to start with what's the most trivial function I could think of to change from 0. We're going to use a 1. Okay, put the cats down. They're all maniacs today. None of them want to cooperate. Apparently they don't want to do differential equations. They did want to do linear algebra. All right, what are we doing with this? Step 1 is I need a homogeneous solution. Step 2 is I need a particular solution. Step 3 is I find the unique alpha and beta that they were talking about using the initial conditions. 1, y homogeneous. This is relatively easy if you know the quadratic formula. You're never going to use completion of squares. Yeah, you are. Yeah, you are on my exams. R squared minus 3r plus 2 equals 0. We have to solve the associated homogeneous equation. Of course, I gave myself nice roots, so I don't have to complete the square. I'm going to anyways, but this is if and only if what multiplies to give me positive 2 and or adds to give me negative 3. We're going to get r minus 1 and r minus 2. And this is one of the problems, or this is one of the issues that comes up that students always ask. Well, what if I made my first one 2 and 1, and what if they get flipped? It won't matter. It's going to fix everything in the problem. We're going to do both right now. What does that tell me? That tells me that based on the theorem, watch the previous videos, but based on this theorem, it says if I have two distinct real roots, I have R1 equals 1 and R2 equals 2, two distinct real roots. The two linearly independent solutions are y homogeneous is C1 e to the x plus C2 e to the 2x. And just in case, yes, right away after I do this one, I'll flip them and it won't matter at all. This is the two linearly independent solutions. This is what we mean by y1, and this is what we mean by y2 now. I have two linear independent solutions. Now let's use variation of parameters for the first time to 2. We need a particular solution. If I use variation of parameters, using variation of parameters, that's going to give me what? I have it memorized, but don't memorize things, derive them. If you derive them enough times, by default, you will memorize them. This is negative 1 over a. A is the coefficient, remember, the integral of f times y2 over the Wronskian, y1, y2, dx. And v2 of x is going to be 1 over a, the integral of f times y1 over the Wronskian of y1, y2. With the Wronskian, just give me a second, we'll do that. So this is what I see as what I have to calculate to compute the particular solution. And where's the role of these guys? That says that y particular, when we do this varying parameters, for varying these parameters, when we do that, this will be v1 y1 plus v2 y2. So before we start, I'll show you anyways, but if you would flip these, it's going to flip the roles of v1 and v2, so you're going to get the same function either way, up to a constant, but then when I use the initial conditions, it will be the same. Let's get to that. What do I need to compute this? I need the a, I need the f, I need y1 and y2. Oh, where is he there? Somewhere in there. And then in this pot is, I need the Wronskian. Who's the Wronskian? It's the determinant of the matrix, which has as the first row the functions and as the second row their derivatives. What? Let's compute. All right, to solve this, we now have the homogeneous solution. Oh, do I have? Oh, that's dice. Oh, a dinosaur egg. A scarabita. Where is it? Come prepared. Oh, what's that? Ah, there we go. I want to keep in mind the homogeneous solution. Wizards have stuff in their pocket. You never know what you're going to need when you solve second order linear constant coefficient non-homogeneous ordinary differential equations using the method of variation of parameters. The Wronskian, after the mathematician Wronski, Polish guy. What we want to do is, this is the easiest way, they give you a formula and students are always like, oh, I'm just going to memorize that y1 prime times y2 minus, no, that's not even it. See, I got it wrong. It's like, don't memorize it, it's a determinant. Set this up every time, and then it's AD minus BC. Determinants are computed. Our function is y1 is this guy, y2 is this guy, so I put them in there in the first row. Then I take their derivatives and I put it in the second row. Then I compute the determinant. That's going to be e to the x times 2e to the 2x minus e to the x times e to the 2x. 2 somethings minus 1 something is 1 somethings, e to the 3x. 2 plus 1 is 3. I've used exponent law. So this is non-zero. They're definitely linearly independent. But what we're going to do with that now is construct v1 and v2. And then from those guys, everyone forgets, we construct a particular solution. Then we have a homogeneous and a particular solution. We'll use the initial conditions to find the C1 and C2 and turn them into alpha and beta. All right, for v1, v1 of x is going to be what? Negative 1 over 1, because a is 1. The integral of 1 times, this is f, and then v1 uses y2, so this should be e to the 2x over the Wronskian, which we already computed was, the Wronskian is a function of x. That's weird. We're saying it's of those two functions, but it's a function of x. There it is. Cleaning that up, I get negative the integral of e to the negative x dx, which is e to the negative x plus c, but we can assume it's 0 when we use the initial conditions anyways. v2 specifically of x is going to equal 1 over a, which is 1, the integral of f of x times y1, which is e to the x, over e to the 3x, the Wronskian. That is, when I clean that up, this is e to the negative 2x dx, which is, taking the antiderivative, is negative 1/2 e to the negative 2x plus another constant. We can assume it's 0. These are v1 and v2. What does that tell us? That tells us y particular of x is v1 y1 plus v2 y2, which is equal to v1 is e to the negative x times y1, which is e to the x, plus negative 1/2 e to the negative 2x times y2, which is e to the 2x. Cancel, 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 cancel. 1 minus 1/2 is 1/2. Particular solution is 1/2. Yeah, I picked an easy function. I want you to be able to see it. If you want, I'll throw in some much harder functions for your exams for you. Now, what does that do? Now I have a homogeneous solution and I have a particular solution. The theorem says the general solution is this guy. All right, so now we have the homogeneous solution, the red pill, and then we have the particular solution, the blue pill. It's like, do we take the red pill or the blue? I can't remember which one it was. I'm going to take both and then do it twice. What we're going to do now is, what did that tell us? The general solution up to the constants. This is the unique solution, but up to the constants we say, and no one understands what we mean. But we're going to get the specific unique solution using these guys. So up to constants, the unique solution is C1 e to the x plus C2 e to the 2x plus 1/2. Remember, this is y homogeneous plus y particular is the solution always. This is the solution, but now to find these guys specifically, I have to use the initial conditions. So that tells me that y of x is C1 e to the x plus C2 e to the 2x plus 1/2. That tells me y of 0 is equal to 1/2. And then what I do is I put 0 wherever x is in this equation. That's going to give me C1 plus C2 plus 1/2. Oh, it's like I cooked this up ahead of time. Those are going to cancel off and I get C1 is negative C2 from the first equation. Then I use this equation to find what these C1 and C2 are. Going to get a system of 2 equations and 2 unknowns, more linear algebra and calculus. What's going on? And then what are we going to get from this? We're going to get y prime of x, first of all, is equal to C1 e to the x plus 2C2 e to the 2x plus gone. And then that means that y prime of 0 is going to be, again, I put 0 anywhere in here, C1 plus 2C2, and that's going to equal 2. What does that give me? I now know I can put that in there. That tells me that negative C2 plus 2C2 equals 2. So C2 equals 2. And C1 was negative of that. So C1 is negative 2. Now I have a unique solution which is guaranteed by our theorem. What is that specifically? Therefore, wrapping that all up, I know now you're excited. Oh, get it. He doesn't want to know the details. It's like the students is like, give me the answer and give me the steps. Okay, step 1, find the homogeneous solution. Step 2, find a particular solution. Step 3, find the initial conditions. Therefore, the unique solution is y of x equals, what is it going to be? You don't care, just chew the pen then. Okay, this is negative 2 e to the x plus 2 e to the 2x plus 1/2. This is the unique solution. Let's do it again. A lot of students are concerned about, what if I made the roots the opposite? So now what does that say? That says y1 is e to the 2x and y2 is e to the x. Well, I still need the Wronskian. The Wronskian of y1, y2 of x this time is the determinant of e to the 2x, e to the x. And then I take their derivatives, 2 e to the 2x, e to the x. That's going to give me e to the 3x minus 2 e to the 3x, which is negative e to the 3x. So we change the Wronskian. Coincidentally, when you change 2 columns or rows in a determinant, you get a negative on the outside of the determinant. Well, properties of determinants, all I've done is flip the rows essentially. So it has to be the same up to a negative. What do I do with the Wronskian? Now, v1 of x is equal to negative 1 over 1a, which is, and then the integral of 1, which is my function f, times y2, which is now e to the x, over my Wronskian, which is negative e to the 3x dx, which gives me the integral, cancel, e to the negative 2x dx, which is negative 1/2 e to the negative 2x. Oh, if you want to come and join. Oh, snuggles. When a cat wants to snuggle, you have to stop for a second and do it. It's a rule. right? Yeah. V2 of x is going to be what? 1 over 1, the a again, the integral of f, which is 1, y1, which is e to the 2x over negative e to the 3x dx, which gives me negative the integral of e to the negative x dx, which gives me e to the negative x. It's almost like they flipped their roles. That tells me that y particular of x is equal to v1 y1 plus v2 y2, which is equal to v1 was negative 1/2 e to the negative 2x times e to the 2x plus e to the negative x times e to the x, cancel, 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 which is negative 1/2 plus 1/2, which is 1/2. It's the same unique function. It has to be. The Wronskian is non-zero, which means Kramer's rule is going to give me a unique solution to these two guys. Anyway, there it is, 1/2. What do I do with that? I put it back in, and I do the exact same thing. What is that going to give me? Our function y of x then is going to be c1 e to the 2x plus c2 e to the x plus 1/2. The derivative of that is going to be 2c1 e to the 2x plus c2 e to the x. That says that y of 0 is 1/2, which is going to be equal to c1 plus c2 plus 1/2. So cancel, cancel, c1 equals negative c2. Y prime of 0 is going to give me 2c1 plus c2 equals 2. We'll flip the roles. c2 is negative c1. Oh, I multiply both sides by negative. Two negatives cancel and annihilate each other. That tells me that I can put c2 as negative c1, so that says 2c1 plus negative c1 equals 2, or c1 is 2 and c2 this time is negative 2. Long story short, our solution is y homogeneous of x plus y particular of x, and with those specific coefficients in there, that's going to give me c1 was 2 e to the 2x minus 2 e to the x plus 1/2. This is the general solution. It's exactly the same as they guaranteed. It has to be unique, so I don't care which method you use. I don't care whether you flip the roots. It's going to be the same. Are we done? No. Let's use the method of undetermined coefficients. Guess what I'm going to get? This. All right, we can do this one more time because this function is a degree 0 polynomial, so it is one of our types of special functions we can apply the method of undetermined coefficients to. So I will, and it doesn't matter which method I used. All that's going to do is find a different method for finding the particular solution. Guess what it's going to be? 1/2. And then it's going to be the same solution. One, I need the homogeneous. So y homogeneous of x, how do I get that? I have the auxiliary equation, r squared minus 3r plus 2 equals 0 if and only if r1 equals 1 and r2 equals 2. We already did that twice. Now what do I use with that? That says that my y homogeneous solution is, because I have two distinct real roots, this will be c1 e to the x plus c2 e to the 2x. The order doesn't matter. Hopefully I've convinced you of this. Once I have the homogeneous solution, what do I need? I need a particular solution. Now let's use the other method, which is undetermined coefficients. 2. F of x, our non-homogeneous part, is function 1, the easiest function I could think of. Therefore, what was our guess? Y particular of x we're going to guess is just a general degree 0 polynomial, which is a number, a. Guess what a is going to be? 1/2. That means that, this is why I did it for myself, yours are going to be horrible functions. You're going to actually have to compute derivatives. You need practice. So do I. I'm never going to stop. Y prime, though, is 0, and yp double prime is also 0. What does that tell me? I put that back in here and I solve, and that's why I made it easy for myself. That's going to tell me that 0 minus 3 times 0 plus 2 times a is equal to 1. What does that give me? Magically, a is 1/2. And so that says y particular is 1/2. Once I have the particular solution, I have a homogeneous solution, I have a particular solution, I have the general solution up to the constants. I'm going to use the coefficient to plug that in. I'll do it one more time. This was the homogeneous solution. This was the particular solution we found using method of undetermined coefficients this time. That says that the general solution, y of x, is equal to
y homogeneous of x plus y particular of x, which is c1 e to the x plus c2 e to the 2x plus 1/2. Now the derivative, y prime of x is going to be c1 e to the x plus 2c2 e to the 2x
plus 0. And then using the initial conditions is equal to, that lured in a kitty. Kitty! So,
what did that tell me? That tells me that this is negative 2 e to the x plus 2 e to the 2x plus 1/2. Then we can
I did it 3 different ways. It doesn't matter which method you use, and whether you put the roots this way or that way, or which method of undetermined coefficients or variation parameters you use. Once you have a homogeneous solution and a particular solution and initial conditions, the unique solution is always this guy. Please subscribe right there. I'll see you next time.